session. First talk by Rhys Davies is on Dirac, gauginos, and F-theory.
Thank you very much. So first of all, let me say thank you to the organisers for a great conference. Thank you to all of you for being here. I'm going to tell you about a paper of mine from just last month from the archive here about Dirac gauginos and gauge unification in the context of F-theory. So first I'll provide some motivation for why Dirac gauginos are a nice thing to think about. Then the second part of my talk will be about the necessary adjoint chiral fields, how these come about in F-theory. If you don't know about F-theory guts, you won't follow that part of the talk, so I apologise, just have a little nap for 3 minutes. But then everybody should understand me here, I think, when I come to talk about gauge unification in this context. Okay. So let me ask the simplest question first. What are Dirac gauginos? Get us all on the same page. So I'm sure you all know this, but if we have a neutral spin-half fermion, then we can give it a Majorana mass, which in a Lagrangian looks like this. On the other hand, if a fermion carries charge, then this term is forbidden. We must introduce a second spin-half fermion eta with the opposite charge and write down a so-called Dirac mass, which can be written in terms of a 4-component Dirac spinor like this. Now in the MSSM, our gauginos are usually assumed to have Majorana masses, but I want to consider the case where for some reason Majorana masses are forbidden. So one nice motivation for this is if, say, there's an unbroken R symmetry at low energies. And if this is the case, then to get masses for our gauginos, we must give them Dirac masses, and to do so we have to introduce some fermions to pair up with them, and for that we introduce chiral multiplets in the adjoint representation of the gauge group. After SUSY breaking, the fermions in these multiplets can pair up with the gauginos to give Dirac masses. So what we end up with in that case is Dirac gauge eno, which I was pretty happy with. Okay, so moving right along, why might we care about these sort of arcane beasts? So to answer that question, let me start with some data. Here's a recent exclusion plot from Atlas. This is based on the full 2011 data. So this is a simplified model of the MSSM. I believe these are bounds on the first 2 generations of squarks. So you can see here, or maybe you can't, these horizontal lines are lines of constant gluino mass, and these vertical lines are lines of constant squark mass. And the take-home message is that gluinos are bounded to be above about 900 GeV, squarks above about a TeV, but we also can't have both that light at the same time. If we ask our gluinos to be down below a TeV, our squarks are already up at around 2 TeV. On the other hand, if we ask our squarks to be below or just below a TeV up here, our gluinos are significantly above a TeV. So in the absence of something like natural SUSY, where the stops are lighter, we've heard a bit about that this week, but in the absence of a structure like that, these models start to look very fine-tuned. So another way around it is to consider giving Dirac masses to our gauginos, and in particular the gluinos are the important ones here. So the difference comes from the quantum properties of these particles. So if we think about the corrections to the Higgs soft mass, which are dependent on the gaugino masses, in the case of a Dirac mass, we get delta mh squared just goes like m squared, where m here is our gluino mass. In the Majorana case, there's an extra log enhancement. Lambda here is the cutoff of the theory. So lambda has to be at least an order of magnitude, generally quite a bit more, above the Dirac masses, the gaugino masses themselves. So you can see the corrections in the Majorana case are much larger. And what this means is we can take Dirac gluinos, which are significantly heavier than the Majorana case, without paying any price in fine-tuning. So let's assume we have these heavy Dirac gauginos. The model's not fine-tuned. What are the implications? Well, due to their special properties and their high masses, we find lower squark production cross-sections at the LHC. And this has the effect of then relaxing these squark mass bounds that I showed. So this has been studied in detail by these authors. This is not my work. And the conclusion I want to emphasize is that models with Dirac gluinos in particular, around 5 TeV, and squarks lighter than 700 GeV, are still allowed by the data. And these are just as natural as MSSM models with everything well below a TeV, but that's already ruled out. So I think this is a very nice alternative to natural SUSY, and one which hasn't really got a lot of attention among string model builders yet.
That's not, what Slippery said there is not ruled out sub-TeV gauginos. There are still some reasons, right?
Well, of course. These are general statements. Yeah. Yes, you can go to certain quantitative parameter states where things are okay. That's true, of course. Okay, so now I want to go through just quickly how we get these necessary adjoint chiral multiplets in F-theory. Those of you who know about F-theory guts will probably know what I'm about to say. Those of you who don't won't understand, so I'll go through this very quickly. So we consider the usual setup, F-theory on an elliptically fibred Calabi-Yau fourfold. If you don't know what an elliptic Calabi-Yau looks like, superpose these two images in your head. That's an elliptic Calabi-Yau. So that gives us unbroken n equals 1 supersymmetry in 4 dimensions. And we choose a special structure for x. We let it have an A4 surface singularity, fibred over some complex surface S. And this gives us an SU5 gauge theory, as Kumran discussed earlier, on the complex surface S. Okay, SU5 is all very well, but it needs to be broken. And following these authors from a few years ago now, we know we can turn on hypercharged flux on this surface to break SU5 down to the standard model gauge group. So we'll assume that setup. And let's ask about where these adjoints can come from. So our theory on S contains a scalar field phi and an 8D gauge field A, which are in the adjoint representation of SU5. We can look at how this breaks down under the standard model group, and you see these first 3 pieces just form the adjoint of the standard model group itself. And in particular, of course, they're all uncharged under hypercharge. They all have 0 hypercharge. And what this means is the number of 0 modes for those fields is completely independent of the hypercharge flux. It depends only on the geometry of S. So in particular, we get chiral multiplets in the adjoint representation. We get H20 of S of them coming from phi. Physically, these correspond to deformations of the brainstack on S. And we get H10 of S coming from the gauge field. These are continuous Wilson lines. So we want one of these or the other. We only want one copy of the adjoint. So we demand that one of these Hodge numbers is 1 and the other is 0. A nice choice for this is to take S to be a K3, which corresponds to this first possibility here. And I'll just note that if we do take S to be K3, or indeed, I think it's a general statement that any of the surfaces satisfying this, we generally won't have a decoupling limit of the sort that Kumran discussed earlier. So there is no limit in which S can be made parametrically smaller than the ambient space B. In other words, in which M gut can be made parametrically smaller than M Planck. But I'll come back to this later. Okay, I think I might largely skip this slide. For those of you who know what I'm talking about, so our hypercharged flux corresponds to some line bundle Ly. We can also have some diagonal flux corresponding to a line bundle La. We can arrange for all this to work out. One nice thing about the K3 case is what are usually necessary conditions for the absence of exotics. So we have these off-diagonal exotics here which we want to get rid of. It's easy to write down necessary conditions for their absence. On K3 they become necessary and sufficient conditions, which is one of the nice things about K3. And we can also easily arrange for the hypercharged flux to leave the hypercharged gauge boson massless. This is all very similar to the D'Alberto case with some small changes. All right, so now on to I suppose my main point. All that was fairly simple for those of you who know about these models. So what about gauge unification? Well, we have an SU5 gut of sorts on S. So you might think the gauge couplings necessarily unify at the compactification scale, but they don't. So Blumenhagen wrote down these relations a few years ago. Donaghy and Weinhold did as well, but I think Blumenhagen did so in a much clearer way. So in particular, I don't really need the details of this expression. All we need to note is that instead of equality of all 3 couplings, we have just a single linear relation between the couplings at the compactification scale. So if we want to talk about F-theory guts in general, this is the only condition we need to impose in the UV. All right, so let's take the standard model gauge couplings as we know them at low energies. Let's put in these extra fields, these adjoint chiral fields, as well as the MSSM spectrum, run the couplings up and see what happens. So the philosophy here is we know what things look like at low energies. We run the couplings up until this F-theory relation is satisfied, until this quantity vanishes, and then we identify that as the compactification scale. You can see here the 3 standard model gauge couplings. They no longer unify because these adjoints don't fill out SU5 multiplets. But we do get this F-theory unification at sort of 10 to the 22 GeV. Now obviously that's no good. That's well above the Planck scale, and that's telling us that we can't get Newton's constant and gauge unification to come out consistently in this way. So we need to fix that somehow. So okay, what we actually need, as I said, the values of these things are fixed at low energies. We have this red line coming down and we identify the compactification scale as that scale where this vanishes. So we need this line to be steeper. In other words, we need a negative contribution to this combination of the beta function coefficients. So let's look at the matter fields that we have available in a typical SU5 model and look at their contributions to this particular combination. So here are our 10 and 5 bar of SU5, their standard model content, and this is a simple calculation to get these combinations of coefficients. And one thing to highlight, which has been pointed out by many authors but with different emphasis I think, is that the two components of the 5 bar here each contribute 0 to this. In other words, it doesn't matter how many of each of these fields I have, I do not change the F-theory unification scale. So these are no good to me for present purposes. It does mean I can introduce whatever I like from this sector as, say, messengers of gauge mediation or something like that without interfering with unification. So there are two multiplets here which have a negative contribution. One of them is charged triplets, coloured triplets I should say. Now you can introduce one vector-like pair of these and keep everything perturbative, but it's nicer to introduce just a single vector-like pair of these singlets. So let's do that. If I do that, if I introduce a vector-like pair of these singlets and give them, for argument's sake, a mass of 1 TeV, this is all very rough, this is all one loop running, no threshold corrections, so all very rough. Give them a mass of 1 TeV, do the running again. Now here's my F-theory line, and we see it hits 0 around about 10 to the 18 GeV. In other words, around about the reduced Planck scale. So if we take this sort of scenario, actually we no longer have any separation really between what we would call the gut scale now and the Planck scale. And so this is perfectly consistent with the lack of a decoupling limit, which I pointed out earlier. Right. So this is completely different to the behaviour of these Del Pezzo-based models. But it is a consistent picture. All right, so I'm running short on time, so let me just summarise. First by pointing out all the things that I haven't done. So for Dirac gauginos to be important, to have these nice properties, we need something to suppress the Majorana masses. And as I mentioned earlier, a nice way to do this is to have an unbroken R symmetry, and there are field theoretic models which do this. In the F-theory situation, an R symmetry like this will come from some geometric symmetry of the compactification. And there's a lot more about this in my paper. It's easy enough to arrange for an appropriate symmetry. We then need to break supersymmetry, obviously, in an appropriate way. I haven't discussed this at all. And in particular, to get large enough Dirac gaugino masses, you really need D-term supersymmetry breaking, or combined D and F-term supersymmetry breaking. So I think there's a lot of work to be done there in deciding whether or not this can be done in a realistic way. Finally, I haven't mentioned engineering a realistic matter sector at all. That's partly because I haven't thought about it a lot. It's also partly because I think a lot of it will go over unchanged from the well-studied case of Del Pezzo surfaces in the literature. So I don't anticipate any major problems here. You might ask, how easy is it to get this vector-like pair of singlets which were crucial to bring the gut scale down? It's essentially a fine-tuned thing. It's essentially a mu problem, right? We have vector-like things, we want them to be fairly light. But you can certainly arrange for it. There are statements in the literature which suggest you can't just pick out one component of the 10 in that way. There's a simple example in my paper which shows actually you can. You can just get a vector-like pair of those singlets if you arrange things appropriately. All right, so finally to conclude, I guess my main point is that traditional SUSY models, which have been used as benchmarks for string model builders for a long time, are already getting seriously squeezed by the LHC, and we need to respond to this in some way, whether it be trying to incorporate natural SUSY models in string theory, which often requires some extra structure, although we heard a nice talk by Hans-Peter Nils on doing that in heterotic model building. An alternative to natural SUSY is to introduce heavy Dirac gauginos. These can be natural even though they have multi-TeV masses, and they have the effect of relaxing the squark mass bounds coming from the LHC. And it seems to me that F-theory is a very natural place to look for models of this type, and I've just taken some very rudimentary steps in that direction. But I hope that other people can pick up this baton and run with it, people with more skills and more time than I have all by myself. So okay, thank you very much.
Piyush.
So can you, what was the mass of these vector-like states to get unification right?
I just gave them a mass of 1 TeV
1 TeV.
for just for argument's sake.
But if you vary it around, it doesn't change it that much. How much does it change?
I mean, you can play with this a lot. This is just an example, without introducing new scales. Right.
So, a related question. I think you were also on the paper with John March Russell with the supersymmetric.
That's right.
There you also have another way where you actually have a 3-bar 2 and a vector-like pair from a 24 of SU5.
Right.
When you break it down into the standard model, you have another way of restoring unification, right?
Right. So I mean, there you're basically just filling out the adjoint of
Yeah.
SU5. I mean, you need some good reason for these states not to cause trouble with baryon number violation and the like.
So have you thought in that direction, or?
Not really. I think it's nicer to project those states out myself. Yeah. These are matters of taste, right? I mean, I could have introduced a lot more states at an intermediate scale to bring the gut scale down. I mean, these are just simple games with free normalization group equations. Nothing complicated.
Okay, let's thank Rhys again.
Thank you.